So in the previous video I have solved the continuous beam. I want to move to the frame structures. Okay, so if you want me to solve more number of continuous beam, I will solve it. You just have to send me a comment in your Google Classroom. So if you are not satisfied with solving the continuous beam, I can solve another two problems, but I thought it was very much clear about the continuous beam, so I wanted to move to frame structures. So I'll just give you one of the frame structure. We'll solve this frame structure. If you would reply me on the Google Classroom to solve more continuous beam problem, I'll solve that also. Okay, anyhow, we'll move on to this structure, which is a frame structure, right? So again, you don't need to worry about looking into the structure, and you should not be able to get shock of this kind of structure. The only thing is that going to the basics, we need to identify the different elements that we have and what are the number of joints we have. Okay, so the joints are A, B, C and D, and joint B is connected by three members, which is BA, BD and BC. It is being connected by three members, and this is joint A and this is joint C, right? So first thing what we need to do is to identify the static independency and kinematic independency. So to do that, what we need to do is to draw the free body diagram of this original frame structure. Okay, taking this same structure over here, now this is your fixed joint. So fixed joint will have two reactions. One is vertical reaction, the other one is your moment reactions MAB, right? So again, going to joint D is subjected to two reactions. One is VD and DB. I've forgotten to write here. Right, so at joint D we will have two reactions, which is VD and MDB, and at joint C we will have one reaction, which is VC. Now while I solve this this problem, at the end I will try to explain how much will be the reaction at joint B. Okay, so now let us try to identify the number of static independency. So first see how many reactions are there. 5 reactions are there, which have to be calculated from the free body diagram. 5 minus 2, 3 is your static independency. Now going to kinematic independency, what we need to do is you need to identify the joint where there can be rotation and translation. So at joint A it is fixed, so there cannot be any translation or rotation, so that's why theta A is equals to 0 there. Now going to joint D, again this is fixed joint, so that's why there is no translation or rotation, so that's why theta D is equals to 0. Now going to joint C, it is a pin joint, so that's why there will be a rotation, but the translation is been eliminated, so theta C exists. Now going to theta B is your internal joint. Internal joints usually go through the rotation, so that's why theta B exists. So the kinematic independency will be 2, and the values of kinematic independency to be calculated is theta C and theta B. It means in this given problem you will have two unknowns. One unknown is EI theta B, the other one is EI theta C, right? So once we understood the static independency and kinematic independency of the structure, what we need to do is to solve the fixed end moments. You separate out all the elements. So this is the first element which has been separated out. This is your member AB. Member AB is subjected to UDL. According to that, you can calculate how much is fixed end moment at AB and BA, which is minus WL square by 12, and this is WL square by 12. So we have calculated how much is MFAB. Similarly, we can calculate how much is fixed end moments for member BC. So this is your member BC. So you will calculate how much is the value of MFBC, which is minus WL by 8. W is 40, L is 4 meter, divided by 8 will give you MFBC. So similarly, you can calculate how much is MFCB also, right? So once you solve this, what you do is you have to take this element, which is your column member. These two are beam members. This is your column member. Take the column, and you try to identify what will be the direction of fixed end moment that will be generated. See, if the load is applied in this direction, this is the direction of fixed end moments that will be generated. So it means this should be negative and this should be positive. But if the scene was opposite to it, so what would have been happen? If the load was acting in this direction, this movement would have been in the clockwise direction. This would have been in the anti-clockwise direction. So in that case, it would have been minus here and plus here. right now the situation is the load is acting in this direction, so that's why these are the direction of fixed end moments which are generated. So that's why this is minus and this is plus. Now let us calculate how much is MFCD. To calculate MFCD, again using the same formula, which is minus of W into L divided by 8, which is minus W is how much, 20 into L. L is 4 divided by 8 will give you the value of MFCD and MFDC, which is 10 and minus 10. So once you solve all the fixed end moments, next thing is to solve the slope deflection equation. Now let us look at the slope deflection equation. We'll first go for joint A. First we need to resolve MAB. So MAB is equals to, as you know, MFAB plus of 2 EI by L into bracket 2 theta A plus theta B minus 3 delta by L is there. As you know, in this structure there is no translation, so the delta by L, 3 delta L will get cancelled out. So this is what the equation is left over. So again in this equation we know theta A is equals to 0. So if theta A is equal to 0, this is what the equation of MAB. You know how much is MFAB, which we already calculated, which is minus 26.67. So substituting that here and resolving this is what the equation I get for MAB. Similarly, we can solve for MBA. Now going to MBC, this is your member BC. As you know, theta B is also existing, theta C is also existing. So MFBC, so how much is MFBC, which is minus 20 plus 2 EI by L. L is 4 meter into bracket 2 theta B plus theta C. After simplifying, this is what my equation. Similarly, I can write for MCB. This is the equation for MCB. Now going to the last member, which is MBD. This is your member MBD. So MBD is equals to MFBD. How much is MFBD? Sorry, I just have made a mistake here. Okay. So this is member BD. So you know how much is MFBD. MFBD is plus 10 plus of 2 EI by 4 into bracket 2 theta B plus of theta D. As you know, theta D is equals to 0. That will get eliminated. This will be the equation for MBD, and this will be the equation for MDB. Okay. So this will be the equation for MDB. So once you solve the slope deflection equation, you know what is the next thing to be done. Okay, once we have solved the slope deflection equation, next thing is to identify the equilibrium equation and solve the equilibrium equation. So as you can see in this board, so we have written two equations. So this becomes my first equation of equilibrium, and this is my second equation of equilibrium. So let us go to this equation. So to solve this equation, what I do is that I go to theta B. So right, so at joint B, we know that the summation of all the moment at joint B should be equal to 0, and similarly the summation of all the moment at joint C should be equal to 0. Let us identify what are the moments that are generated at joint B. So the moments that are generated at joint B are MBA plus MBC plus MBD will be equal to 0. So that's how I written the equation, MBA plus MBC plus MBD equal to 0. So as you know, we have already solved what is MBA. So this is my equation for MBA. I substituted that. Similarly, MBC has been substituted here, and MBD is also been substituted in this equation. After simplification, this is what the first equation I got, right? So the next thing is to solve MCB equal to 0. So we know what is MCB equation. So I have rewritten the MCB equation here, and I called it as equation 2. So from these two equations, I have determined how much will be the value of EI theta B and EI theta C. So once you solve the unknowns, which is theta B and theta C, we have to substitute back into the equation of slope deflection and solve how much is the end moments. So MAB is minus 27.78, so MBA is 24.245, and MBC is minus 31.815, and MCB is equal to 0 because we already considered MCB equal to 0. MBD is equals to 7.575, MDB is minus 11.2125. So we have determined all the end moments. So in the next class, we will be solving the reactions VBA, VD, VC, and we'll also try to draw the shear force diagram and bending moment diagram for this given problem. Okay, so all of you try to solve the reaction VA, VD and VC. Okay, by next class or by next video, you can comment the reactions that you have calculated. Okay, so you try to solve this, you solve the reactions VA, VD and VC, and you try to send it in the comment section. Okay, thank you very much.